Okay, hi everybody. May I ask to turn on your camera, please? Thanks. I appreciate it if more of you turn on your camera so I can see you guys and better communicate with you, so I can follow whether the material that I cover it makes sense or not. That is very helpful. So the plan today is to start talking about interesting topic in computer architecture, which is called microarchitecture. This is the most fundamental topic in computer architecture, I would say. Is an important layer in the stack that we discuss, and we will from this week we will cover several different basically aspects of microarchitecture as we continue. So it's a slightly different from previous topics to some extent. It's obviously different from assembly programming. It's more about implementation, hardware implementation, but it's also at the same time exciting, and I believe it provides some contextual information for you to grasp the whole idea about computer architecture in general, I would say. Before we start, do you have any question about anything that I can clarify?
Can you go over JAL, jump and link, and how to use that properly with the function?
Sorry, what is the question?
Can you go over jump and link?
Now?
I mean, after the class is over, of course.
We start a new topic. We can discuss that after lecture. How about that?
Yes, sir.
Is there any other question? That's great. Few other information. You will hear soon about the next homework. So hopefully before the midterm, I plan to give you guys 2 more homeworks, so you get familiar and to expect what you will see in the midterm. But there would be no extension like the first homework. Please make sure to complete the homework on time and submit it on time. But I would happy to provide any help as always for you to succeed and learn better. And within this month, we'll have the midterm. I will announce the exact date for that. Make sure, because one thing that I noticed, some of you, I realized, which is unfortunate, some of you do not really follow this course. I realized based on the emails that I received, some of you not even know the basic stuff. That's fine. Not knowing is fine, but basically it's not fine if you do not ask question as early as possible, so I can clarify things for you. I can help you. it's no good if you know, by the exam I know that, okay, you do not know even like what is the textbook of this course, the basic stuff. That's not fun. So please make sure that you follow the lectures, the basic stuff, and as always, I would be happy to provide any help if needed. Okay, let's continue. So again, these are some readings that you can look it up. Mainly, if you are interested to know more about microarchitecture, I would highly suggest to read chapter 7 of the textbook that we have. Also, if you're interested more about knowing microarchitecture, you can look it up, Patter's book, to read more, but these are optional, up to you if you want to understand and know more about microarchitecture, which is exciting. Both single cycle and multi-cycle microarchitecture. And next, we will continue the discussion after we are done with this basic stuff about microarchitecture. We'll continue to see what are the opportunities to improve performance. And performance again is very important in computer architecture, and designing microarchitecture is a way to improve performance. Again, like I would to emphasize trade-off. In computer architecture, trade-off is super important. We discussed about trade-off several times. The trade-off that we discussed was mainly concerned about instruction set architecture, different way that we can define this interface. But in addition to that, in the microarchitecture level, there are even more important trade-off aspects, design points that help designers to design microarchitecture that really take into account different aspects of performance, specifically, for example, the execution time, given some constraint about power and cost, for example. We'll discuss in more detail, hopefully today and next lecture. Performance is very important. Yes, Ras?
I was just going to ask if you'd be willing to maybe like go over the homework after class. Maybe not this lecture, but like I think a lot of us are going to continue to struggle if we don't know what we did wrong, or if some of us even have no idea, which is fine. But if you go over it, I think that'll help a lot of us, and I would appreciate it a ton. I think a lot of us would.
Absolutely. Awesome. Thanks for mentioning that. I wanted to hear this. Like I wouldn't do that if you didn't ask for it, right?
Right.
I'm honest. Thanks for asking.
Of course, thank you.
I will do that. I will announce it. Let me see how we progress. I would like to do that as soon as possible. Either would be next lecture, at the end of next lecture, or an extra session that I will announce it maybe over weekend or sometimes. But I'll find some good time, so hopefully most of you can attend. And this is very important to make sure if that's fine, again, not succeeding in the first homework, as I mentioned, I will drop the list scores from the whole homework that you will get. But it's always good to learn what mistake you made and so on. But it's even better after we grade them and the grade. So after we discuss, things become a lot more clear. Fantastic. That's very good. So basically, pipelining is again one of those important way of improving performance that we'll discuss. And after these, for example, pipelining, we'll discuss some advanced topics in computer architecture, such as out-of-order execution, which is one of those interesting topics which violates Von-Neumann model, but also provide a lot of performance opportunities. We'll discuss when after that. So it takes like a few weeks until we get there. But from this slide, you see like the path so far, and like until several weeks ahead of us, right? So far we discussed about ISA, instruction set architecture, and assembly programming extensively. Now we'll talk about microarchitecture and specifically multi-cycle microarchitecture next, and the next is obvious. So you know about Von-Neumann model. Right, these 5 different components: memory, input, output, processing unit, and control unit. We discussed that. We also, beside the Von-Neumann model, discuss about machine that implements Von-Neumann model. Make sure you understand the differences, relationship, right? So LC3 was one of those machines. MIPS also was one of those machines, both implementing Von-Neumann model. We discussed this, and also we discussed instruction cycle, fetch, decoding, evaluation, fetching operand, execution, and storing the result. This is the instruction cycle. And microarchitecture is essentially is a way to implement this instruction cycle with the more detail about the logic design and so on. And this is the whole stack. Again, we discussed about this stack. I would like to emphasize that and position where the microarchitecture is, right? So we discussed about the problem specification, designing algorithm, writing program. The ISA is the interface between upper layers in the stack where programmers care about. And ISA define this interface to make sure that we have a contract that programmers can rely on and write their program. So this contract would not change over time. So, and we discussed why it is important to have such contract, because if contract changes, everything above needs to also be changed, right? So the contract is fixed. Layers down there, microarchitecture, circuits, electrons, right? Microarchitecture is an implementation of this contract. And we could have obviously different implementation of the same contract. We'll talk about this in more detail, but basically microarchitecture is an important part of this stack that we will elaborate as we continue. And we discuss about like the building blocks of the ISA, memory organization, register set, instruction set. These are like these are important parts of the ISA, right? And essentially, if you think about this, is nothing but some bunch of instruction and architecture state. And we discussed about this, right? Specifically, architecture states are the register set and the memory, what is in the memory, and instruction set tells, okay, like how the architecture, when we execute the instruction, how the architecture state are going to be changed over time as new instruction get executed. So microarchitecture is an implementation of the ISA, this lecture, several lectures down the line, we'll discuss how we are going to implement an ISA, because there would be simply many different implementation of the same ISA. For example, for even MIPS, there are so many different implementation of that. For example, R2000 is like a very simple implementation of MIPS, and is like you know, single instruction, simple hardware. But R10000 is also implementing MIPS ISA, but has more sophisticated way of improving performance using multi-cycle instruction and microarchitecture and so on. So basically, we have different implementation of MIPS. Also the same for like x86 type of ISA. We have different different implementation of that, like so many of them, right? And for sure you're familiar with these machines, Pentium. Pentium was very popular at my time when I was in college, but AMD, K5, K7, K9, and so many other different implementation of x86 type of ISA. So again, these are different implementation, different microarchitecture of the same contract. Okay, some on trade-off. Again, I asked you this before, and we discussed that very extensively, because it is really important that for you to know the fundamental properties of Von-Neumann model. And these fundamental properties are two of them. Programs are stored in memory the same way as we store data. Also, instruction are processed sequentially, okay, one by one. So these are like fundamental, important two key properties of Von-Neumann model. So we have a linear memory, which also store, in addition to data, instructions as well. And basically there is, from the computer's perspective, there is no difference between instruction and data. Like if you look at the memory, is linear. But we have a way of like, and you know that how when we know part of the memory is instruction, we know how to interpret that. ISA providing us the way to interpret part of the memory, which, for example, for MIPS, 32 bits, if we are given 32 bits and we are, and somebody asks, okay, like this is instruction, interpret it, we can. If you look at the ISA and the coding of different instruction, we are able to decode this instruction. But essentially, there is no difference between instructions and data. So if nobody tells us that this is instruction or data, we cannot say like what it is. Could be either. Okay. And we know that we have program counter that points to a specific or current instruction that needs to be executed. And program counter is advanced sequentially, except there's a specific instruction, for example, jump, where jump the program counter to another place rather than the next memory address. So we discussed that. You know about this. Okay, nothing new here. And now let's discuss quickly another model. To clarify, this is another model that we are going to discuss, which is different from Von-Neumann, has totally different properties. And the key reason, motivation for introducing this quickly is for you to, again, have another example that Von-Neumann model is not really the only way that we can or we could build computers. There are obviously different ways of building computers. But essentially, this is Von-Neumann model is the dominant paradigm for computing. And it has been the dominant paradigm for so many years. No doubt, and this is for a reason, because of simplicity of this model. But there are other way of building a computer, which we are going to talk about, that essentially violates these two properties of Von-Neumann, which basically the program will execute it sequentially. In this model that is called Dataflow order, there is no program counter that points to the current instruction. So there is nothing that needs to be maintained. Where is the current instruction? And the execution of the instruction happens based on the availability of the inputs, right? Or essentially when the operands are ready. Each instruction has different operands. So when the operands are ready, all of its operands, it can get executed. So there is no instruction pointer, or there is no program counter, and availability of the operands determine when an instruction can execute. And in this model, the benefit is that instruction can really get executed at the same time because of this model. Okay. Imagine that you have like n different instructions, like out of these n instructions, maybe 10 of them, their operands are ready at the same time. So they can go ahead, like get executed at the same time within this model, which violates totally the Von-Neumann, where instruction can only get executed one by one after another. And program counter like tells which instruction needs to get executed now. So hopefully you see the differences. And it's important to identify these differences again for you to have yet another different way of thinking, a possibility of building a computer. Here is, for example, very simple example of a program that like does some operation. We add B to A, we put it to V. We do some several operations sequentially. In the sequential order as we have, but in data flow way on the right hand side. So here you see we have on the top we have operand A and B. We have two operations, add and also multiplying to 2. Okay, so if you imagine this, these two instructions, add and multiplying to 2, if A and B are ready at the same time, if like we can feed A and B at the same time, these two operations can get executed at the same time instead of like first adding A and then multiplying B by 2. These can get executed at the same time. And like mathematically, if you think about it, there's no like dependencies between these two. Okay, look on the equation on the left hand side, adding A and B and multiplying B by 2. Do they have any dependency? No, so they can get executed at the same time. In Von-Neumann model, we have to execute this one by one. In Dataflow model, not really. As long as there is no dependency, you can execute them in parallel. The only time that you need to wait if there is a dependency. Okay. For example, we cannot execute this until we have V and W. Okay, V and W coming from here and here. Okay, so there is a clear dependency in order to get this, and also this one. Okay, so again, these two instructions, these this line for getting X and Y, these two can executed in parallel on the middle. You see here, as soon as you get the result of addition and multiplying by 2, you can execute the next two in parallel. If basically you can your computer can get the result of this addition and multiplication at the same time. Okay, assuming that you can produce these two at the same time, these two, the next two instructions, since they have no dependencies between each other, they can get executed at the same time. And then obviously this multiplication, the last instruction, depends on both X and Y. So we have to wait until the last instruction gets executed. So in this, you clearly see that in an ideal way, there is like three steps, or essentially there are some parallelism that you see here. Like we can execute the first two together, the second two instruction together, and the last one needs to be wait until the end. Okay, Do you have any question about this? So again, Dataflow is yet another way of building a computer, but obviously this is going to be difficult, and for us even it's difficult to think that way, right? I mean, for this program is simple, but for generic program, figuring out dependencies like is going to be difficult unless we have a tool for us to make this dependency explicit, so we can program naturally that way, but without any tools, it's for us humanist programmers is really difficult to think about data flow types of writing programs, and even like implementing such type of model from the hardware side is also very complicated, and that's why this type of building computers has never become popular. There has been some attempts of building such computers, but like all of them were failed. But it's good again to have this contrast, that knowing that there are possible way of like building, having yet another model beside Von-Neumann. Again, this is more along the line of enabling you guys to think about trade-off.
Somebody had a question in the chat.
Oh, okay. How do we know subtract v minus w and not w minus v? Oh, you mean, okay, good question. This is very good question, thanks. This is, again, similarly, these are encoded in the encoding parts, right? So here, like, you see, like, here we have multiplication, right? So we have two arguments, arg1, arg2. We know what are these, and also whether they are ready or not, and where we want to send a result. Okay. For obviously multiplication, mathematically doesn't matter which one it is, but for negating or for subtracting, it matters, like which one is which, but we know the ordering, right? So we know like what is the arg1, the left arrow coming to this node, what is arg2, the right arrow. So here we know that, right? So we know the left side is produced by addition, v here, and the right side is produced by multiplying to 2 w. So v come here, w come here. So like we know which is which, like left minus right. Could have been encoded differently, right? But as long as we know the encoding, the math works. Does that answer your question, Stephen?
Yes, it does. Thank you.
Good question. And again, similarly, similar to the way how we define all of these encoding, like here, like some schematic aspect of this encoding, like for example, for conditional, like we have branching, we get the data signal. We also get whether the control signal. Okay, if the control signal is true, the data will be passed to like somewhere in the program. If this is false, like it goes somewhere else, right? So this branch node controls like where you want to send the data, okay? Whether you want to send it like in one node in the program or the other node in the program. So this way you have a way of like building a general purpose program. Also like some other relational nodes, like whether like this argument is larger than the other argument based on which like based on which you go where, right? So there are some nodes that you need also barrier thinking where basically produce the signal if all of them come at the same time. So to synchronize the signals. So you have some nodes similarly to write a program that you want to write. And here, for example, an example of such program that you can write. So again, like here you get a number. Yeah, a bunch of nodes here again, and you get one here, right? So you get n here. Then you have copy. Okay. So you copy n. N is a like integer. Imagine it's an integer. So let's interpret what's going on. So you copy this n. If it is larger than 0, okay, you, for example, let's say it's 2, okay. If 2 obviously larger than 0, you copy that. So basically, copy this result of comparison, right? It's either false or true, okay? So if it's 2, this is going to be evaluated as true, okay? And it sends this signal to these 2 branch as a control signal, right? So you see that this branch requires a control signal and the data signal. Remember we discussed this? Like this is control signal, this is data signal. So the data for this branch is 1. The data for this branch is what? Somebody says? I'm waiting because I want you to follow. What data comes here?
The Boolean result of greater than 0?
No, I'm talking about the data. The control signal is obviously coming here, which for this
break?
was true. What?
Is it the break?
Yes. So basically, what data comes to this node is a branching node.
Or branching, not breaking. Sorry. Yeah.
What data comes here? It's very easy. See, the interpretation was here, right? So the data come from top. This is the control signal. Follow this path.
Copy?
Is what?
A copy?
So n gets copied here, right? So n gets copied here. So meaning that copying, meaning like you send a copy of n to all of these multiple branches, right? Both here and both here. This branch is a node, a comparison node, is this node, okay? So this comparison says that this is, if this number that I got here, whether it's larger than 0 or not. In our case, let's say n is 3. Let's imagine n is 3. We send 3 here and 3 here. This says that if 3 is larger than 0, yes, we copy true to all of these, to both these nodes. So I'm asking what data we get here. Come on, it's very simple.
Just a copy of n?
What copy gives what number exactly for this example?
If we're working with 3, it'd just be 3.
Exactly. So it's 3, simple. Because we send this copy, send the signal of 3 to both of these nodes, I told you, right? So we get 3 here. This branch says that, okay, like let's imagine here, like look at here. What number we get here? 1, right? So we get 1. What Boolean we got here for this example? True.
True.
Okay. So this, what this does is sending 1 where? It's sending 1 here, right? So because it was true. If it was false, we are out. Okay. Now we got true, so it sends this number here. Let's see what number comes here, right? So this multiplication basically required 2 number coming to this node. So from here, we got 3 here. This was true. So we come here, sends 3 here to copy, basically copy 3 and send it to both. This node is decrement, basically decreasing 3 by 1 and sending the result back here. So this node sending 3 minus 1, which is 2, sending back up. And this node again sent 3 here to this multiplication node. We got 3 here. We got 1 here. 3 multiplication to 1 is 3, sending 3 back up. Where?
It sends it over to the beginning of the break on the left side, all the way around.
So you see that clearly it travels here. We get 3 here, okay? So at the beginning, we got 1. Now we got 3 here. What we got here, you remember?
We have 2 there now.
2. Can you guess what this program does based on this instruction that we followed in one cycle?
It just counts down from n to 0, just repeats that loop n times and then exits the program.
And what value we get here at the end?
We get the product of all of those numbers.
What are these numbers if we product, we multiply them together? It's factorial, correct. So This is a program that generates a factorial of a number that we put here, right? So we put 3. Factorial of 3 would be 6. Sorry, 6, right? If we put 4, we get factorial of 4, meaning that 4 multiplying 3 multiplying 2, 5, the same way, 6, you can follow the same, okay? So this is a program in Dataflow paradigm that does factorial. You can write another program that does other things, right? Using this combination of nodes, okay? Again, this is like, as long as similar to MIPS, similar to LC3, as long as you know how to interpret each node, meaning that if you know the semantic of the nodes, and if you know how these connections, how these nodes gets executed, basically knowing the data flow paradigm, meaning that as soon as the operands of a nodes are ready, the instruction can get executed. You are able to interpret and follow the execution of a program, and you're also able to write a program. Yes.
Do you worry about like recursion at this level, or is that only really at a level where you'd be using like C? Would you be trying to implement recursion, or would you worry about that at like a low level like this? Just because factorials, like you usually see it, like I feel like I usually see it being done recursively in like high level languages.
Yeah, I mean, you can also write recursion in assembly, right? So writing recursion, as long as you can emulate a function, which you remember we discussed about emulating a function in assembly is not really a construct that giving us the function. We needed to emulate a function in assembly. So we can write recursion in assembly. The same way we can write recursion here. We somehow, if you think about it, we somehow, in a way, by connecting these, we emulated a function. A function is basically multiplication here of 2 numbers, which one of them, basically we emulated here a kind of recursion, right? In general, by the way how these nodes are connected. If you think these recursions has been enabled by these 2 feedback, feedback that we send back to the input, right? So we have an input here. We basically send back the result of the output to the input. Somehow we emulated the recursion here by the way how we interconnected nodes, right? So if there was no feedback, this was somehow, there wouldn't be any recursion. But since we have feedback, like these feedback connections are a way to emulate recursion with in Dataflow programs, right? The same way in assembly, the same way in, if you think in high level. In high level programming languages, like we have the construct of a function explicitly. Here we don't, but like we have nodes that we can put together in a specific way to emulate a function and also recursion. Does it make sense?
Yes, thank you.
Sure, good question. Okay, that's good. That's good that we discussed about data flow again. For now, take it into account that you have a alternative model in mind to contrast. So more about this, right? So I mean, this is easy question. Do we need an instruction pointer in ISA? Yes, if it is control driven, if it is sequential order, like Von-Neumann, but if it's data driven, like the Dataflow model, you don't really need program counter or IP or PC, right? Both of them are the same. You saw that like as soon as the operands are ready, you can execute an instruction no matter where it is. And there are like these two paradigms, there are different trade-off again. Ease of programming, obviously it's a lot easier to write a sequential program. Ease of compilation, probably since compilers are sophisticated, I mean, you can write sophisticated compilers to make this compilation happen easily. Obviously, there are performance trade-off. Once you have parallelism, hopefully you get a better performance since you execute things together at the same time. On the other hand, for hardware complexity, obviously it's going to be a lot harder, more complex to construct a hardware that implements, for example, data-driven paradigms like Dataflow paradigm that we discussed. And that's why, like, we do not have successful implementation of Dataflow because it's so complicated and makes things very complex. So there are certainly different trade-off is going on. And similarly, since we discussed about control data-driven execution trade-off, the same sort of trade-off is going at the microarchitecture level. To repeat, ISA, instruction set architecture, is specifying what programmers sees essentially have access to this instruction, that programmer can have access and write their program. Microarchitecture is the way how we implement these instructions, the way how these instructions are going to be executed. And if you think clearly about this, you can define an interface and you somehow experience it before, for sure. Like when you are writing a function, if I give you a task, write a function that does a specific thing, and I give you an interface, give me this function with this interface. Each one of you are going to write this function very differently, okay? That has like different performance, like different ways. I mean, probably some of you write it in a way that it's not producing the right output, but mostly you will write a program that produces the right output, but it works differently, okay? But all of you know the interface. As long as you stick to the interface, you come up with different implementation. This is the same here. ISA defined that interface. Microarchitecture is the implementation that execute these instructions, right? So for each instruction, microarchitecture implements, okay, like when I have add, how do I implement this add? When I have like another instruction, how do I implement another instructions, okay? So hopefully this relationship is clear for you, because it's important. Programmers don't care about microarchitecture, like it's not visible to them. Only care about the ISA. Microarchitecture microarchitecture basically can violate even some of the assumption, as long as it can provide, it can stick to the contract, okay? And we'll see that like at the microarchitecture, we'll see that some of the implementation even violates Von-Neumann assumption, Von-Neumann properties, but it still is the correct implementation of like the MIPS ISA. So you can do things differently at the microarchitecture, because this is not really visible to programmers. Programmers can assume like however like they put the instruction, like they get executed one by one. Okay, one after another, unless there is a jump. So they know like where next instruction, even after the jump, going to get executed. So they have the right paradigm in their mind when they write program. But in microarchitecture, at the microarchitecture level, like you can mess around with everything, as long as you stick to the contract and emulate this, emulate somehow this perspective to the programmer, that programmers assume that everything is all right, even though down the line you do some messy stuff. You may sometimes violate some of the key properties. So this is the relationship between these two. Okay. Any questions so far? Again, I would like to emphasize these are very important part of microarchitecture and the whole course. If you're not clear about anything, do ask for it. I'm happy to provide more info. Is there any question here? Okay. Yeah, and some of these different implementation, like for example, pipeline instruction execution in Intel, like happened in 486 microarchitecture. Multiple instruction at the time happened implemented in Intel Pentium, out of order execution in Pentium Pro, separate instruction at data caches and so on. And some of these really violate these Von-Neumann properties that we'll discuss later on. So don't need to be worried about this, but these are some of these examples. and again, not exposed to the programmer. It's like the mess that is hidden below the ISA. And we discussed about like this traditional definition of computer architecture and this more modern definition of computer architecture, like having a traditional way was only looking at the ISA level, the contract, but this modern is basically making this implementation of the ISA very explicit, making this performance trade-off very explicit and important part of the computer architecture. And why we need to have this broader perspective of computer architecture, not only the ISA level. Okay, I guess we have, how much time we have? We have discussed about this. Let me see what, because we have another important I wanted to discuss. Oh, this is also a good example, right? So that help you to interpret, again, having another example, distinguish between like ISA and microarchitecture. Like in cars, like all cars, almost all cars, you have this gas pedal, okay? Like by default, no car you sit, except those that have like acceleration by hand, which is weird. You have, gas pedal that you can right away, no matter whether this is an electric car or gas-based cars. No matter what, like if you push the pedal, the car will accelerate. But how this engine gets implemented is totally different in electric cars than the gasoline, right? Gasoline-based engines. So this interface, gas pedal is the interface, is the ISA. The internal of the engine, the implementation of the engine is the microarchitecture level. So that's a good example for you to distinguish between these two, and also like another example, like for more technical example for add instruction. Like you can have many different way of implementing it in the logic design, right? So I'm sure in previous courses you had this type of, like, for example, implementing an adder, and you have different way of implementing it with bit serial, ripple carry. Again, these are like the way how you implemented a particular logic gates, right? But at the end of the day, the functionality that you get at the whole block is to add two numbers together. The way how you implement it, bit serial, like bit by bit, or all bits at the same time, with some other details, is just implementation details. Give you the same semantic, but with different types of implementations. Okay, let me also discuss quickly one important other aspect of this before we finish up. But we'll discuss more later on. That's a strange. I'm not sure why it doesn't allow me to. To share this, but I will explain it maybe in more detail next time. I have some slide, so maybe I can, because I wanted to explain it on the iPad with some notes so you can get this important concept better, but we can also do it through slides. Which is about performance analysis. And this is also an important topic, basic, that we'll touch several times. We discussed it briefly, but it is also important, very important when it comes to microarchitecture, which is about how fast program runs on a computer, right? And there are different factors that determine performance. These factors are, and this is also a simplistic way of thinking about performance. There are like multiple perspectives of performance, but this is very useful perspective to interpret performance. Of interpreting, every program consists of obviously a series of instructions, and each instruction needs to be executed, right? And these instructions are realized on the hardware, and they take one or more clock cycle to complete, right? So, I mean, when we will continue with the microarchitecture, we start by a single cycle where each instruction takes one cycle. This is the assumption. But then we'll discuss, okay, why this is not an ideal, why with this single cycle we cannot get the best performance, because simply like the cycle will be determined by the slowest instruction, which is not really good if we write a general purpose program, because like we may not use even that slow instruction at all, but our performance will be determined by the slowest instruction that is implemented in the computer that we are writing the program, okay? And why this performance trade-off is important, we'll discuss in more detail later on. But I just wanted to introduce some terminology here. So, for example, cycle per instruction, the number of cycles that it takes to implement, to execute an instruction, it's called CPI, and also how much time is spent in one cycle. And this is determined by the critical path in a cycle, like it's called clock period. And 1 over clock period is clock frequency. And this is like what you see always in the CPU specification, like what is the clock frequency of the CPU, right? How many cycle can be done in each second, okay? You are familiar with this clock frequency. And don't worry if you do not fully understand this, I'm going to use my iPad next time and explain in detail like what are each of these terminology and how we can interpret it. So again, like once when we have a program, it has n instruction, and our processor needs a specific cycle for each instruction. Let's imagine CPI cycles, right? And the maximum clock speed of the processor is f, meaning that the clock period is 1 over f or t. The program execution time is n multiplying by CPI by t, right? So overall is n multiplying by CPI by t seconds it takes to execute this program. Okay, so we have n instruction. CPI was the number of cycles for each instructions, and the maximum clock speed of the processor was f. So 1 over f determined the clock period. So the clock period multiplied by the number of cycles multiplied by the whole number of instruction determine the execution time or performance of the program that you write. And this is very important fundamental formula to think and use when it comes for performance analysis, and to give you the reason why maybe it is important to distinguish between two parts of this formula. One part is n, the number of instruction. One part is CPI multiplying by t. And if you think about it, why it is important, and corresponding it to the whole stack that we discussed, you realize why. But let me briefly mention, if you think about ISA, what determines the number of instructions that you need to write a program? So what part of this, the whole stack determines the number of instructions that you need for writing a program like n factorial, like adding two numbers or whatever? What part of this stack determines the number of instructions? Is easy, the ISA, right? So ISA could be could give you very sophisticated instruction or very simple set of instructions, right? Sophisticated instruction might be giving you even high-level stuff, right? Maybe multiplying two arrays, which typically they don't. But also might give you a lot of very simple instruction, like MIPS, this kind of risk reduced instruction set type of paradigm that we discussed. So obviously with risk, you need to use more instruction. With CISC, you can write your program shorter, right? So you get a smaller n. But on the other hand, in risk type of models where you have a lot of simple instruction, you can have a better CPI and you can have a better t, shorter t. But on the other hand, in more complex ISA, these numbers would would increase, right? So you need larger CPI in order to implement this complex instruction as a result, and also obviously the maximum clock speed also would basically, this T1/F, the maximum clock speed would basically decrease, and the T would increase as a result because of this complexity. Even for the same ISA, I mentioned there would be different implementation. Each implementation could change CPI or T, right? This N for one ISA, this N would be fixed, because like for MIPS, like you can write a program with a fixed number of instructions, right? For a specific instruction, right? Obviously, you can implement, for example, let's say n factorial different way. But let's imagine that, like in an ideal world, we can write n specific instruction in order to implement a function. The part that varies performance is like how I'm going to implement these instructions, how I'm going to have my microarchitecture performance, and why there are different microarchitecture implementation, because of this performance trade-off, because each implementation changes CPI and T, so this performance trade-off happens. I'm going to discuss this further next time, but for now, let's stop here. I would be happy to answer any question if you guys have. Again, this performance is very important part of the course, so make sure that you follow.